Welcome to Lesson 7 of the Basic Electricity module. In this lesson, we'll cover batteries, how they work, their types, characteristics, maintenance, and safe servicing practices. A battery is made of two or more cells that convert chemical energy into electrical energy. Primary cells can't be recharged. Secondary cells, also called storage batteries, can be restored by applying current. The most common battery in use today is the primary cell or dry cell, such as AAA, AA, C, D, etc. Carbon-zinc cells are the most common primary cells. They produce 1.5 volts regardless of size. Larger sizes supply more current. Alkaline cells last longer and deliver more current than carbon-zinc. They have reverse polarity due to zinc and manganese construction, but still follow standard terminal markings. Mercury cells are small, high-capacity alkaline cells used in compact devices. Their polarity is also reversed, similar to other alkaline cells. Unlike primary cells, secondary cells can be recharged. They don't generate electricity, but store it chemically, hence the term storage batteries. Lead-acid batteries are common in aircraft. Each cell gives about 2.1 volts. Plates are immersed in sulfuric acid and separated by porous material to allow fluid movement and sediment collection. During discharge, electrons move from negative plates to positive. Lead sulfate builds up, and the electrolyte becomes diluted, making it prone to freezing. This diagram illustrates the chemical changes that occur during the discharge of a lead-acid battery. When the battery delivers current to an external load, such as lighting a bulb, electrons flow from the negative plate to the positive plate through the external circuit. Inside the battery, the negative plate is made of lead, and the positive plate is lead peroxide. Both plates are submerged in an electrolyte made of sulfuric acid and water. During discharge, sulfate ions from the electrolyte combine with both plates, forming lead sulfate. At the same time, the lead peroxide at the positive plate reacts with hydrogen ions to produce water, and oxygen is released into the electrolyte. As a result, both plates become coated with lead sulfate, and the sulfuric acid concentration in the electrolyte decreases. This chemical transformation reduces the battery's voltage output as discharge continues. These reactions are reversible during the charging process, which restores the original chemical composition and energy potential of the battery. Charging restores the plates to their original state. Sulfuric acid concentration increases, reducing freeze risk. Charging also releases hydrogen gas. During the charging process of a lead-acid battery, electrical energy is supplied from an external power source, reversing the chemical changes that occurred during discharge. As current flows into the battery, electrons are forced back toward the negative plate. At the negative plate, lead sulfate is converted back into pure lead. At the positive plate, lead sulfate is converted back into lead peroxide. Meanwhile, sulfate ions return to the electrolyte, combining with water to rebuild the sulfuric acid concentration. This restores the battery's electrolyte to its original strength and reverses the water formation that occurred during discharge. The charging process effectively regenerates both the active materials on the plates and the strength of the electrolyte, restoring the battery's ability to deliver electrical energy in future cycles. Proper charging is essential to prolong battery life and maintain optimal performance. Voltage alone doesn't show battery charge. Instead, specific gravity is measured. A fully charged battery has a specific gravity of 1.275 to 1.300 at 80 degrees Fahrenheit. Below 1.150 means discharged. During battery testing, use a hydrometer to measure electrolyte density. The float's height in the liquid reflects the specific gravity. Denser electrolyte gives a higher reading. In this image, We see a technician using a hydrometer to check the specific gravity of the electrolyte in a lead-acid battery. This test is an important part of battery maintenance. By drawing a sample of the electrolyte into the hydrometer, the technician can measure its density compared to water. The specific gravity provides a direct indication of the battery's state of charge. A fully charged battery typically reads around 1.265, while a discharged battery may fall to around 1.120 or lower. Significant differences between cells could also indicate internal damage or sulfation. It's important to perform this test carefully and wear appropriate protective equipment, as the electrolyte contains sulfuric acid. Regularly checking specific gravity helps ensure the battery remains healthy, balanced, and capable of delivering reliable power when needed. This slide shows a correction chart used when determining the specific gravity of a battery's electrolyte. Since electrolyte density changes with temperature, the reading obtained from a hydrometer must be corrected if the temperature is different from the standard 80 degrees Fahrenheit. As temperature increases, the electrolyte becomes less dense, resulting in a lower reading. Conversely, colder temperatures make the electrolyte denser, which gives a higher reading. This chart helps you apply the appropriate correction factor. For example, if the temperature is 100 degrees Fahrenheit, you would add 8 points to the reading. If it's 40 degrees Fahrenheit, you would subtract 16 points. Accurate correction ensures a true indication of the battery's state of charge and helps prevent misdiagnosis during maintenance checks. In rating a battery, each cell has an open circuit voltage of 2.1 volts. Internal resistance increases when lead sulfate forms. Use Ohm's law to calculate internal resistance during discharge. Battery capacity is the amount of current a battery can deliver over time, measured in ampere hours. It's influenced by plate area, electrolyte, active material, and temperature. 5-hour discharge is the standard capacity rating. Higher discharge rates reduce capacity due to heat, sulfation, and localized electrolyte dilution. This table shows the discharge characteristics of 12-volt and 24-volt batteries, each with 9 plates per cell, under various load conditions. The discharge rate is categorized into 5-hour, 20-minute, and 5-minute intervals, each showing both ampere hours and the corresponding current in amps. For example, a 12-volt battery can deliver 25 ampere hours over 5 hours at a rate of 5 amps. But if discharged over just 5 minutes, it supplies 11.7 ampere hours at a much higher current, 140 amps. Similarly, a 24-volt battery delivers 17 ampere hours over 5 hours at 3.4 amps, and 6.7 ampere hours over 5 minutes at 80 amps. It's important to note that a battery is considered fully discharged when its closed-circuit voltage drops to 1.2 volts per cell. Understanding these values helps technicians determine the battery's condition, capacity, and whether it can handle specific operational demands. To test a battery cell, measure the voltage of individual cells under load to identify weak ones. Good cells should read about 1.95 volts and be within 0.05 volts of each other. Now let's focus on servicing and charging the battery, starting with cleaning. Keep batteries clean and terminals tight. Use a baking soda solution to neutralize corrosion, rinse thoroughly, and protect terminals with grease. In servicing the battery, add only distilled water, not acid, when electrolyte is low. Most new batteries need a slow boost charge before use and electrolyte adjustment afterward. As part of routine battery servicing, it's important to check the electrolyte level inside each cell. This illustration shows the internal structure of a battery filler cap. The arrow points to the built-in indicator that helps guide electrolyte filling. The electrolyte level should rise just enough to reach this indicator. If the level is too low, it can expose the plates to air, causing sulfation and reducing battery capacity. If overfilled, the electrolyte may spill or overflow during charging, leading to corrosion or dilution. Always top off with distilled water, never acid, and only after charging the battery, unless the plates are already exposed. Accurate electrolyte levels ensure reliable battery performance and extend service life. Note the following important safety tips. Always add acid to water, not the reverse. Wear protective gear to prevent burns or splashes from battery acid. Charge the battery by applying DC opposite to discharge current. The charger voltage must be higher than battery voltage to overcome internal resistance. Also note that batteries are charged by either the constant voltage or constant current method. For constant current charging, use a fixed current, typically no more than 7% of battery amp-hour rating. In charging multiple batteries, connect them in series if they need the same charging rate. Constant voltage charging uses a fixed voltage just above battery voltage. Works best for batteries with the same voltage connected in parallel. Current flow depends on battery's charge state. As a precaution, charge in a ventilated area to avoid hydrogen gas buildup. Turn off the charger before connecting or disconnecting leads. Disconnect the negative lead first during removal. During battery installation, use the correct battery type. Most aircraft use a single-wire system grounded to the airframe. Always connect the positive lead first, and disconnect the negative first. Fumes should be properly vented. Nickel-cadmium batteries maintain voltage almost until fully discharged. However, their low internal resistance can cause thermal runaway if not managed properly. NiCad batteries use potassium hydroxide as the electrolyte. Since the electrolyte acts as a conductor, not energy storage, its specific gravity doesn't indicate charge level. This image shows an individual cell from a nickel-cadmium, or NiCad, battery. Unlike lead-acid batteries, NiCad batteries are constructed from separate, individual cells, each housed in a transparent or translucent case. This design makes it easy to visually inspect the electrolyte level and internal condition of each cell without opening it. NiCad batteries are widely used in aviation due to their durability, long cycle life, and excellent performance in extreme temperatures. They are particularly well suited for high discharge applications like engine starting. However, they require careful maintenance, especially with regard to cell balancing, venting, and electrolyte management, to prevent issues like thermal runaway or cell reversal. Regular servicing and proper charging techniques are essential to keeping these high-performance batteries operating safely and reliably. During discharge, the plates absorb electrolyte, lowering the level. After charging, the electrolyte level rises. Always check levels after full charge. Charging nickel-cadmium batteries causes electrolysis and gassing. Electrolyte reaches its highest level immediately after charging. Add water only when the battery is fully charged. To balance charge between cells, charge partially with constant voltage, then finish with a constant current to prevent excessive gassing and ensure full charge. During NiCad servicing, keep NiCad and lead-acid battery servicing areas separate. NiCads may develop potassium carbonate deposits. This image shows a technician performing a cell-to-case leakage test on a nickel-cadmium battery using a milliammeter. This test checks for unwanted current leakage between the battery cells and the metallic case, an indication of contamination or electrolyte residue. To perform the test, one probe is connected to the cell terminal and the other to the case. A reading above 100 milliamps is considered excessive. Such leakage can cause electrical faults, compromise safety, and lead to corrosion or performance issues. If the leakage exceeds this limit, the battery must be disassembled and thoroughly cleaned. Proper cleaning and reassembly help restore insulation and ensure the battery operates safely and efficiently. Routine leakage testing is a vital part of NiCad battery maintenance and should never be overlooked. Burn marks on cell hardware indicate improper torque. Check all connections carefully during inspection. The only accurate way to determine the true condition of a NiCad battery is to fully charge it, then discharge it at a specific rate to measure its ampere-hour capacity. If the battery delivers less capacity than expected, it indicates an imbalance between the cells. In such cases, the battery must undergo deep cycling, a controlled process of full discharge and recharge to equalize the cells. Once the battery is fully charged, and immediately after it's removed from the charger, measure the electrolyte level. This is because NiCad plates absorb electrolyte during discharge, or when the battery sits idle for extended periods. Lastly, if you observe water and electrolyte spewing from the battery during charging, it's a clear sign that water was added prematurely while the battery was still in a discharge state. This overfilling leads to expansion during charge, causing overflow. Proper servicing ensures safety, longevity, and optimal performance of the battery system. This image shows a nickel-cadmium battery with shorting straps installed across the cells, a procedure used during deep discharge servicing. When the voltage of each cell drops to approximately 0.2 volts, the cells are considered nearly fully discharged. At this point, shorting straps are installed to ensure all cells discharge completely and equally. This step is critical because any imbalance between cells can lead to poor battery performance and shortened lifespan. Equalizing the discharge across all cells helps maintain uniform capacity and prevents overcharging or reversal during recharging. This practice is part of deep cycling, a standard maintenance procedure used to restore balance and maximize the effectiveness of NiCad batteries. Let's take a closer look at some additional aspects of nickel-cadmium battery servicing. NiCad batteries can be charged using either the constant voltage or constant current method. Although the constant voltage method charges the battery faster, it is the constant current method that is most commonly used in aviation due to its control and consistency. As a NiCad battery nears the completion of a charge, it naturally begins to release gases. This is a normal part of the charging process and must occur before the cell is considered fully charged. It's also important to note that the actual voltage of a fully charged cell can vary depending on both the temperature and the charging method used. These factors must be taken into account when evaluating the state of charge and during performance testing. Understanding these behaviors ensures proper charging, prevents damage, and promotes longer battery life. This image shows the Christie Reflex Charger, an industry-standard device used to perform charging, discharging, and analysis of nickel-cadmium batteries during deep cycle maintenance. To complete the deep cycle operation, the battery must be recharged to 140% of its rated ampere-hour capacity. This overcharge ensures all cells reach full charge, and that any cell imbalances are corrected through equalization. The analyzer section of the unit monitors current and voltage, allowing precise control during both discharge and recharge phases. Proper use of this equipment ensures safe, consistent servicing and prolongs battery life. Following this final charging step, the battery is ready for return to service or storage under recommended conditions. This concludes Lesson 7 on batteries. You've learned how batteries work, the differences between lead-acid and nickel-cadmium types, and how to properly test, service, and charge them. As an aviation maintenance technician, proper battery care ensures safe and reliable aircraft operations. Always follow manufacturer guidelines and safety procedures when handling batteries. See you in the next lesson.